For the vast majority of human history, our solar system seemed to end with the gas giants. But in 1930, a young astronomer named Clyde Tombaugh peered through a telescope and noticed a tiny, faint speck of light drifting slowly against the backdrop of distant stars. This was Pluto, a world so far away that it appeared as little more than a pinprick of light. For decades that followed, it remained a profound enigma, a lonely outpost on the very fringe of our known cosmic neighborhood. Its immense distance from Earth made it incredibly difficult to study, leaving scientists with more questions than answers. It was a place of speculation, a cold, dark, and likely uneventful world, or so we thought. Our best images of Pluto, even from powerful instruments like the Hubble Space Telescope, were frustratingly blurry. They showed a small, fuzzy orb with indistinct patches of light and dark, hinting at some surface variation but revealing no real detail. From these observations, scientists pieced together a rudimentary picture. Pluto was thought to be a simple, geologically dead body, a relic from the early solar system frozen in time. The prevailing theory was that it was little more than a cratered ball of ice and rock, having long ago exhausted any internal heat it might have once possessed. Its thin atmosphere was expected to be a simple, static layer of gas, perhaps freezing and collapsing onto the surface as it moved further from the sun. This perception of Pluto as a static, inert world shaped our expectations for what we might find there. It was classified as a planet, but it seemed to lack all the dynamic characteristics we associated with one. Planets like Earth and Mars have active geology, volcanoes, tectonic plates, and weather systems that constantly reshape their surfaces. Even the moons of Jupiter and Saturn showed signs of incredible activity, with icy geysers and hidden oceans. Pluto, however, was thought to be different. Its small size and vast distance from the sun's warmth suggested it had been in a deep freeze for billions of years, a silent testament to the cold, unchanging nature of the outer solar system. This view of Pluto as a simple, frozen artifact was the scientific consensus for over 80 years. It was a logical conclusion based on the limited data we had. A small world, so far from the life-giving energy of the sun, simply shouldn't have the power to drive complex geological processes. But science is a journey of discovery, and our understanding is constantly evolving, often in the most unexpected ways. The story of Pluto is a perfect example of this. The quiet, distant point of light we had watched for so long was about to challenge everything we thought we knew about the icy worlds at the edge of our solar system, and it would do so in the most spectacular fashion. To solve the enduring mystery of Pluto, humanity had to do something audacious. We had to go there. This was the genesis of NASA's New Horizons mission, one of the most ambitious voyages of exploration ever undertaken. Launched in January 2006, the spacecraft was designed to be our first robotic emissary to this distant realm. It was a marvel of engineering, a compact probe packed with sophisticated scientific instruments, each with a specific purpose: to map Pluto's surface, analyze its thin atmosphere, and measure its temperature. It was a mission born from decades of curiosity, a direct attempt to turn a faint dot of light into a tangible, knowable world. The journey itself was an epic undertaking, a testament to patience and precision. New Horizons was the fastest spacecraft ever launched, hurtling away from Earth at incredible speeds. Yet, even at this velocity, the voyage to Pluto took 9.5 long years. For nearly a decade, the probe travelled across the vast expanse of our solar system, crossing the orbits of Mars, Jupiter, Saturn, Uranus, and Neptune. For most of this journey, the spacecraft was in a state of electronic hibernation, silently coasting through the void to conserve power and protect its systems for the critical encounter that lay ahead. It was a lonely vigil in the dark. As New Horizons drew closer to its destination in the summer of 2015, The anticipation within the scientific community and around the world was palpable. The first images it sent back were already a revelation. The blurry dot we knew began to resolve into a distinct sphere, and then features began to emerge. A large, heart-shaped region appeared, a stunning and unexpected welcome sign from the edge of the solar system. Each new image was sharper than the last, revealing a world of stunning complexity that no one had predicted. The mission was no longer just about collecting data. It was about witnessing the unveiling of a new world for the very first time. The climax of this incredible journey occurred on July 14, 2015. On that day, the New Horizons spacecraft executed a flawless flyby, racing past Pluto at over 31,000 miles per hour. During this brief, intense encounter, which lasted only a few hours, its instruments worked furiously, gathering as much information as possible. It was a one-shot opportunity. There would be no second chance to orbit or return. The probe had traveled for nearly a decade and across 3 billion miles for this fleeting moment. The precious data it collected would then begin its long, slow journey back to Earth, promising to rewrite the story of Pluto forever. The first detailed images from the New Horizons flyby left scientists utterly astonished. The world that was revealed was not the static, crater-pocked ice ball that had been predicted. Instead, Pluto was a vibrant and dynamic place, full of breathtaking and bewildering geological features. Perhaps the most shocking discovery was the presence of colossal mountains. These were not gentle, rolling hills, but jagged, towering peaks, some rising as high as the Rocky Mountains on Earth. What made this so astounding was that they appeared to be made of water ice. On Pluto, where surface temperatures are incredibly low, water ice is as hard as rock, strong enough to support these immense structures. But the mountains were just the beginning. The spacecraft's cameras revealed a stunningly diverse and youthful landscape. There were vast, smooth plains of frozen nitrogen, sweeping valleys, and even fields of dunes, suggesting that winds may blow across Pluto's surface. One of the most remarkable features was a massive glacier, officially named Sputnik Planitia, that forms the western lobe of Pluto's famous heart. This enormous sheet of exotic ices, primarily nitrogen, methane, and carbon monoxide, showed clear signs of flow, much like glaciers on Earth. The surface was divided into polygonal cells that appeared to be slowly churning, a sign of convection, indicating that heat was bubbling up from beneath. This discovery of a geologically active surface was a profound paradigm shift. For a world as small and as cold as Pluto, such activity should not be possible. Geological processes on Earth are driven by heat from our planet's core, but a small body like Pluto should have lost its primordial heat billions of years ago. The youthful appearance of many of its surface features, particularly the lack of craters in regions like Sputnik Planitia, implied that the surface was being actively renewed. This meant that parts of Pluto's landscape were geologically young, perhaps only a few million years old, which is the blink of an eye in cosmic terms. The implications of this were enormous. It suggested that Pluto must have some kind of ongoing internal heat source, a mechanism to power this unexpected geological engine. Scientists began to speculate about what this source could be. Perhaps it was the slow decay of radioactive elements within Pluto's rocky core, a process that could provide a steady, long-lasting supply of warmth. Whatever the cause, the flyby had transformed our understanding. Pluto was not a dead world. It was alive with geological activity, a complex and evolving place that challenged our fundamental theories about how small, icy worlds behave in the cold, outer reaches of the solar system. Among the most captivating discoveries on Pluto was the vast, heart-shaped feature officially known as Tombor Regio. Its western lobe, Sputnik Planitia, turned out to be the key to understanding Pluto's surprising vitality. This enormous basin, stretching over 600 miles across, is not a static sheet of ice. Instead, it behaves like a gigantic lava lamp. The plain is composed of a deep reservoir of frozen nitrogen, methane, and carbon monoxide. Deeper down, modest heat from Pluto's interior gently warms the bottom of this icy layer. As the nitrogen ice warms, it becomes less dense and slowly rises to the surface in large, buoyant blobs. Once at the surface, this ice cools over millions of years, radiating its faint heat into the cold vacuum of space. As it cools, it becomes denser and eventually sinks back down along the edges of the large polygonal cells visible on the surface. This process, known as solid-state convection, is a slow but constant churning that continually resurfaces the plane. This is why Sputnik Planitia is so smooth and virtually free of impact craters. Any craters that form are effectively erased over time as the icy surface renews itself. This beating heart of ice is the engine driving much of the geological activity we see on Pluto, a stunning example of planetary processes occurring in the most extreme cold. The activity within Sputnik Planitia has a profound effect on the rest of Pluto. As the nitrogen ice turns into vapor in the thin sunlight, it contributes to Pluto's surprisingly complex atmosphere. The New Horizons mission discovered that Pluto's atmosphere was not collapsing as predicted, but was in fact layered with hazes, creating a beautiful blue glow when backlit by the sun. These hazes are thought to be complex organic molecules, created when solar radiation interacts with the methane in the atmosphere. This atmospheric activity, driven by the sublimation of ices from the heart-shaped glacier, helps to transport materials and may even create winds that shape the planet's surface. Furthermore, scientists found evidence of what appear to be ice volcanoes, known as cryovolcanoes. Two large mountains, Wright Mons and Piccard Mons, have deep central depressions, much like shield volcanoes on Earth. However, instead of spewing molten rock, these structures may have once erupted a slushy mixture of water, ammonia, or other ices from Pluto's interior. The existence of cryovolcanism would provide further evidence of an internal heat source, powerful enough to melt these exotic ices and drive them to the surface. It paints a picture of Pluto as a far more complex and dynamic world than anyone dared to imagine, with a living, breathing geology powered by its icy heart. Section 5. Whispers of a Hidden Ocean. Perhaps the most tantalizing possibility raised by the New Horizons mission is, well, the idea that Pluto might harbor a vast ocean of liquid water beneath its frozen crust. This concept, once considered science fiction, is now a leading hypothesis supported by several lines of evidence. The primary clue lies once again with Sputnik Planitia. This massive basin is located in a position that suggests it is a positive mass anomaly, meaning it is heavier than the surrounding terrain. Now, this is quite counterintuitive. A giant impact crater should have less mass. The best explanation is that the basin is filled with dense material, and a subsurface ocean of liquid water, which is denser than ice, fits this model perfectly. The theory goes that a large object struck Pluto long ago, creating the basin. As the crater formed, it thinned the icy crust. This thinning allowed water from a subsurface ocean to well up from below, pushing the crust upward. Over time, the basin filled with slightly less dense nitrogen ice, but the upwelling of the denser liquid water from beneath would still create an overall mass concentration. This extra mass would have caused the entire dwarf planet to reorient itself over geological time, shifting Sputnik Planitia to its current position near the equator. This reorientation is a powerful piece of indirect evidence for a hidden ocean. For liquid water to exist, there must be a source of heat and some kind of antifreeze. The heat could come from the slow decay of radioactive elements in Pluto's rocky core, a process that has likely been ongoing for billions of years. This alone might not be enough to keep water liquid, but scientists believe the ocean may be rich in ammonia or other salts. Just as salt lowers the freezing point of water on Earth's wintry roads, these compounds could act as a natural antifreeze, allowing the ocean to remain in a liquid state, even at the frigid temperatures found deep inside Pluto. This combination of gentle heat and chemical antifreeze could sustain a liquid layer hundreds of kilometers thick. The implications of a subsurface ocean on Pluto are, well, profound. On Earth, wherever we find liquid water, we find life. While the conditions in Pluto's ocean would be extreme, dark, cold, and under immense pressure, the possibility that it could host microbial life cannot be entirely dismissed. It fundamentally changes our perspective on habitability. It suggests that the necessary ingredients for life might not be confined to rocky planets in the Goldilocks zone around a star. Instead, life could potentially exist in the dark, hidden oceans of icy worlds throughout the cosmos, powered by internal heat rather than sunlight. Pluto, once a symbol of the cold, dead outer solar system, may instead be a signpost for a new, hidden frontier for life. Pluto does not travel alone. It is, in fact, the most famous resident of a vast, icy region beyond the orbit of Neptune known as the Kuiper Belt. This distant realm is rather like a cosmic deep freeze, containing trillions of icy bodies, remnants from the formation of our solar system some 4.6 billion years ago. Before the New Horizons mission, the Kuiper Belt was, well, largely theoretical, a sparsely populated zone of small, inert cometary objects. We thought of it as the solar system's attic, a dusty, quiet place where primordial building blocks were stored, unchanged since the dawn of time. Pluto was simply the largest of these objects, a king in a barren kingdom. The discoveries at Pluto, however, forced a complete re-evaluation of this picture. If Pluto, a dwarf planet, could be so geologically active and complex, what about the countless other large objects in the Kuiper Belt? Worlds like Eris, Makemake, and Haumea, which are also classified as dwarf planets, might not be the simple frozen balls of ice we assumed. They too could have internal heat sources, subsurface oceans, and dynamic surfaces. The Kuiper Belt was transformed in our imagination from a graveyard of cosmic debris into a vibrant landscape of potentially active worlds, each with its own unique story waiting to be told. It is now seen as a third zone of our solar system, distinct from the inner rocky planets and the outer gas giants. After its historic Pluto flyby, the New Horizons mission continued its journey deeper into this mysterious region. In 2019, it performed a second flyby, this time of a much smaller Kuiper Belt object named Arrokoth. This object, shaped rather like two flattened pancakes stuck together, provided a pristine glimpse of what a planetary building block looks like. Unlike Pluto, Arrokoth appeared to have been preserved in its original state, never having undergone significant geological processing. This contrast between the active Pluto and the primordial Arrokoth highlights the incredible diversity of worlds that exist within the Kuiper Belt. It is, truly, a region of both ancient relics and evolving worlds. Even today, in 2025, as New Horizons travels ever further from the Sun, it continues to make groundbreaking discoveries. The spacecraft's instruments are now being used as a unique observatory, studying the outer solar system from a vantage point no other probe has reached. Recent data has hinted that the Kuiper Belt may be even larger than previously thought, or that there might be a second, more distant belt of objects. These findings are transforming our understanding of how planetary systems form, suggesting that the outer edges of our own solar system are far more extensive and complex than our models had predicted. The Kuiper Belt is no longer the end of the line. It is, in fact, a new frontier. The strange and wonderful nature of the Kuiper Belt has given rise to one of the most exciting astronomical mysteries of our time: the search for a hidden planet. As astronomers have mapped the orbits of the most distant objects in the Kuiper Belt, they have noticed something peculiar. A handful of these small, icy bodies follow highly unusual paths. Their orbits are elongated and tilted in a similar direction, as if they are being shepherded by the gravitational pull of a large, unseen object. This clustering is statistically very unlikely to be a coincidence, leading many scientists to believe there is another planet lurking in the dark, far beyond Pluto. This hypothetical world has been given several names over the years, including Planet 9 and, more recently, Planet Y. The latest calculations, announced in late 2025, suggest that the evidence for this planet's existence has grown stronger. Based on the tilted orbits of these distant Kuiper Belt objects, astronomers infer that Planet Y could have a mass somewhere between that of Mercury and Earth. It is thought to be orbiting the Sun at an immense distance, perhaps 100 to 200 times farther out than Earth, on a path that takes thousands of years to complete. Its gravitational influence, though weak from so far away, would still be strong enough to sculpt the orbits of smaller bodies over billions of years. Finding this planet, as you might imagine, is an enormous challenge. Because it would be so far from the Sun, it would reflect very little light, making it incredibly faint and difficult to spot with even our most powerful telescopes. Scientists are essentially searching for a gravitational ghost, an object whose presence is felt but not seen. The search involves meticulously scanning huge patches of the night sky, looking for a single, slow-moving point of light among a sea of countless stars and distant galaxies. It is a painstaking process, really, like finding a single dark needle in a truly cosmic haystack. However, we are entering a new era of astronomical capability that may soon turn this hypothesis into a direct discovery. The Vera C. Rubin Observatory in Chile, which is set to begin its decade-long survey of the sky in late 2025, is poised to be a game-changer. Its powerful telescope will repeatedly scan the entire southern sky, cataloguing billions of celestial objects. This unprecedented survey is expected to discover thousands of new Kuiper Belt objects, providing a much clearer map of the outer solar system's gravitational landscape. Within the next few years, the Rubin Observatory could find the definitive evidence for Planet Y, either by directly imaging it or by revealing its influence on so many objects that its existence becomes undeniable. Despite its historic successes and ongoing potential for discovery, the New Horizons mission faces an uncertain future. As of 2025, the spacecraft remains healthy and fully operational, continuing its journey through the uncharted territory of the outer heliosphere. It is one of only 5 probes to have ever reached such a distance, and one of only 3 that is still functioning. It provides us with a unique eye on the distant solar system, measuring the environment and searching for other Kuiper Belt objects. Its continued operation is crucial for understanding the true extent and nature of this vast region, a scientific endeavour that is far from complete. However, the mission has recently come under threat due to proposed NASA budget cuts. Operating a spacecraft across billions of miles of space requires significant resources, including the dedicated time of large radio antennas on Earth to receive its faint signals. As priorities shift and new missions are developed, there is always pressure to reallocate funding. The potential shutdown of New Horizons would be a profound scientific loss. It would mean silencing our only probe currently exploring the outer solar system, effectively closing our window onto the Kuiper Belt just as we are beginning to grasp its complexity and importance. The scientific community, led by organisations like the Planetary Society, has actively campaigned to save the mission. They argue that the cost of continuing to operate New Horizons is a tiny fraction of the cost of building and launching a new mission to the outer solar system. The spacecraft could continue to return valuable data well into the 2030s, eventually crossing into interstellar space and joining the Voyager probe as our third messenger to the stars. Its instruments can study the boundary where the sun's influence ends and the galactic environment begins, providing invaluable data that can only be gathered on site. This debate over funding highlights a perennial challenge in space exploration, balancing the desire for new discoveries with the need to support ongoing missions. The story of New Horizons is a powerful reminder that a mission's value does not end after its primary objective is complete. The extended journey is often where some of the most unexpected and transformative discoveries are made. The fate of New Horizons will determine whether we continue to listen to the whispers from the edge of our solar system, or allow this intrepid explorer to fall silent just as it is venturing into a new, unexplored frontier. The discoveries made by New Horizons at Pluto and beyond represent a monumental leap in our understanding of the cosmos. They have shattered old paradigms and opened up exciting new avenues for exploration. We now know that the potential for active, dynamic worlds is not limited to the warmer, inner regions of a solar system. Icy bodies, long dismissed as inert relics, can harbour internal heat, complex geology, and even the most essential ingredient for life, liquid water. This realization forces us to broaden our search for life, looking toward the hidden oceans of icy moons and dwarf planets, both in our own solar system and in the countless planetary systems beyond. The ongoing search for Planet Y is a direct consequence of this new understanding. The Kuiper Belt is no longer just a collection of debris, but a complex, structured region whose architecture may be telling us about a missing member of our own planetary family. Confirming the existence of another planet in our solar system would be a discovery of historic proportions, fundamentally altering our map of home. It would provide a natural laboratory for studying how planets form and migrate, and it would raise fascinating new questions about the origins and evolution of our cosmic neighborhood. The next few years, with the power of observatories like Vera C. Rubin, promise to be a thrilling chapter in this cosmic detective story. Looking forward, the legacy of Pluto will inspire the next generation of missions. Scientists are already dreaming of returning to the outer solar system, not for a fleeting flyby, but with orbiters and landers. Imagine a mission that could orbit Pluto, mapping its surface in stunning detail and watching its atmospheric cycles over time. Imagine a lander touching down on the soft nitrogen ice of Sputnik Planitia, drilling beneath the surface to search for clues about the hidden ocean below. Missions are also being designed to visit other dwarf planets like Eris and Makemake, and to explore the moons of Uranus and Neptune, which may also harbour subsurface oceans. Ultimately, the story of Pluto is a story about the nature of exploration itself. It reminds us that our universe is filled with surprises, and that our assumptions are often just placeholders for a more wonderful and complex reality. We explore not just to find answers, but to discover better questions. The journey of New Horizons transformed a distant point of light into a living, breathing world, and in doing so, expanded the realm of what we thought was possible. It is a powerful testament to human curiosity, a journey that has not only taken us to the edge of our solar system, but has also brought us to the brink of a new understanding of our place in the universe.